Interfaces and polymorphism. Interfaces are one of Go's most powerful features. Unlike Java or C#, there is no implements keyword. If a type has the right methods, it automatically satisfies the interface. This is called implicit implementation. In this video, you will learn how interfaces work, type assertions, type switches, and the important principle of accepting interfaces and returning structs. An interface defines a set of method signatures. Any type that has all those methods satisfies the interface automatically. Here, the shape interface requires area and perimeter methods. Both circle and rectangle implement these methods, so they both satisfy shape. Notice that neither type declares it implements shape anywhere. With interfaces, you can write functions that accept any type satisfying the interface. The printShape function takes any shape and calls area and perimeter. You can pass a circle, rectangle, or any future type that has those methods. This is polymorphism, one function working with different types through a shared interface. Implicit implementation matters because you can define interfaces after the types exist. You can create an interface for types from other packages, even standard library types. Small interfaces are easy to create. The type does not need to know about the interface. This design reduces coupling and encourages small, focused interfaces. The empty interface has no methods, so every type satisfies it. Since Go 1.18, you can use the keyword any instead of interface curly braces. They mean the same thing. Use any sparingly because it turns off type checking. Prefer specific interfaces whenever possible to keep your code safe and clear. A type assertion extracts the concrete type from an interface value. The single value form panics if the type does not match. Always use the two-value form with the OK boolean to safely check the type. If OK is true, the assertion succeeded. If false, the value is 0 and you can handle the error gracefully. A type switch checks the type of an interface value using the .type syntax. It is cleaner than multiple type assertions. Inside each case branch, the variable v gets the correct concrete type, so you can safely use type-specific operations. This pattern is common when processing values of unknown types. You can combine small interfaces into larger ones through interface embedding. The Go standard library does this extensively. The I/O package defines reader, writer, and closer as small single-method interfaces, then combines them into readWriter and readWriteCloser. This composability is a key strength of Go's interface system. The FMT, stringer interface, has a single string method. If your type implements it, FMT, println will use your custom string representation. The error interface also has a single method called error. You can create custom error types by implementing this method on a struct. These two interfaces appear everywhere in Go code. To make a collection sortable, implement the sort interface with three methods: len, less, and swap. Create a named type for your slice, then attach these methods. In modern Go, you can also use sort slice with a closure, which is simpler for one-off sorting when you do not need a reusable sort type. An important Go design principle is accept interfaces, return structs. Functions should take interfaces as parameters for flexibility. This way, any type with the right methods can be passed in. But return concrete types so callers get full access to all methods. This pattern makes your code flexible yet specific. Here is a practical example: a notification system using interfaces. The notifier interface has a single notify method. Email notifier, SMS notifier, and Slack notifier each implement it differently. The broadcast function takes a slice of notifiers and sends a message to all of them. Adding a new notification type requires no changes to existing code. This is the power of interfaces. You define the behavior you need, and any type can provide it. The broadcast function does not know or care about the concrete types. It just calls notify on each one. This is how Go achieves polymorphism without classes or inheritance. The first common mistake is making interfaces too large. A 20-method interface is hard to implement and test. Go proverb says, the bigger the interface, the weaker the abstraction. Keep interfaces small, ideally 1 to 3 methods. You can always compose multiple small interfaces into a larger one when needed. The second mistake is returning an interface instead of a concrete type. When a function returns an interface, the caller loses access to methods that are not in the interface. Return concrete types so callers get full functionality. Accept interfaces in parameters for flexibility, but return the real type. The third mistake is forgetting the OK, check, and type assertions. If you use the single value form and the type does not match, your program panics at runtime. Always use the two-value form with the OK Boolean. This turns a runtime crash into a controlled check that you can handle gracefully in your code. Let us review. Interfaces define behavior through method signatures. Implementation is implicit, no implements keyword needed. Use small interfaces and compose them. Accept interfaces in function parameters. Return concrete types. Use the OK pattern for safe type assertions. These principles make Go code flexible and maintainable. In the next video, you will learn about pointers in Go. Pointers let you share and modify data efficiently. You will learn the ampersand and star operators, pointer receivers, nil pointers, and when to use pointers versus values. Go pointers are simpler than C pointers because there is no pointer arithmetic. If you like this video, hit the like button and subscribe for more tutorials.